The next person up is also the last person up. But it is an excellent person, so woo! Excellent, spontaneous applause, I like that. So our final speaker is wending his way to the front of Metrics now, or the back. I don't know if this is probably really the back, I don't know. Anyway, the front of the makeshift auditorium, and it is Matt Staniford, who is a PhD student at the University of Southampton. His PhD is on the maths of carbon nanotubes, and he'll be telling us all about them. Matt used to work for ISIS, which is the neutron spallation source at Rutherford Appleton Laboratories in Harwell, Didcot, and his talk is on nanomaterials made easy. Thanks.
Okay, cool. So, yeah, I don't know. I'm Matt Staniford. I'm a PhD student at Southampton University. I'm a little bit different from both Andy and Jacek, who both already spoke, in that I'm a student, not a kind of researcher already. The upshot of being a researcher at any kind of academic institution is that whenever you Google anyone's name that is a researcher there, you get kind of instant sort of results on exactly who you're talking about. For example, if you look at Andy Bannon, here's the guy himself. This is, you look at Google Images, and then if we go on, we go to Jacek, and there he is, the very same picture that both of them used for this talk. Unfortunately, the thing about being a PhD student is that whilst I do have a slightly unique name, you sort of look up Matthew Staniford, you unfortunately get a small child singing on YouTube, which was not actually me, but I'm second place, so I'm not quite at the top of Google search just yet. But okay, so I do something called algebraic topology, and the thing about algebraic topology is a little bit of a balance between the two things that have been spoken about already this evening. So Andy spoke a lot about space, and Jacek spoke a lot about shape and curvature. And I kind of live in the gap between the two things. So I do this thing called algebraic topology. If you try to look that up anywhere, you'll get a definition that looks a little bit like this. This is kind of one of the problems with trying to look up anything technical about maths or science or anything else. You Wikipedia, you do anything else, you'll get something that's basically indecipherable. I mean, what any of that means is unknown to anyone other than people who already know exactly what you should be talking about. Which is kind of where we come in, right? Like people who are kind of here to explain it to you, okay, none of what makes sense. I mean, what's topology? I mean, homology, homotopy, like, there's no real explanation there, is there? Apart from the words themselves. So again, from the horse's mouth, it's essentially the study of complicated shapes in space using the tools of algebra. Now, what does that really mean? I mean, it's kind of like, we look at abstract things that don't necessarily exist in the real world, or sometimes they do, and we study them using the tools of algebra. So things that you can't necessarily visualize, sometimes higher dimensional or lower dimensional things, and we kind of pick them apart using the tools of algebra. A good example, which is something that you actually can realize in the real world, is something called the Borromean rings. What's interesting about these things is if you imagine these guys were metallic rings that were all linked together, look at any individual two of them. The blue and the green rings, if you forget the red ring, are not connected. The blue and the red and the green and the red are not individually connected. But when you bring them all together, they are connected, they form a sort of knot. And these are known as the Borromean rings, and they're kind of fascinating. They're an interesting shape in the sense that they're not connected. Almost anything, when you connect two things together, sort of the two of them by themselves will be fine, but three things here are necessary to make these things into a sort of knot. And these are one of the kind of small examples that we kind of study using algebraic topology, but I'm not going to say too much more about that tonight. Algebraic topology has applications to such a large area of different things that it really, it's kind of inconceivable. I've only mentioned a few of them here. One of the very popular things at the moment is, one of the things I haven't mentioned is that I play chess. I'm very interested in chess. A neural network computer that was invented recently by Google is called AlphaZero. I don't know if anyone in the audience has heard of that. I'm looking for nods, and I can't see. Oh, I can see one or two. Okay, that's good. AlphaZero is a computer that was essentially built to play chess, but the fascinating thing about it is that it wasn't told any of the rules of chess before. It wasn't taught. Sorry, that's wrong. It was taught the rules, as in what it is legal and not legal to do, but it wasn't taught any of the strategy of chess. It was simply taught the rules and said, okay, play yourself. And it did that, and within 24 hours, it beat the best computer in the world. which is known as Stockfish. Stockfish has been being developed for the last 15 to 20 years. It's not a neural network computer, it's a kind of human intervention, kind of programmable computer that's been being sophisticatedly developed, and within 24 hours, this neural network, which is AlphaZero, which Google developed, beat Stockfish. And algebraic topology has a lot of applications to neural networks and this kind of data analysis stuff. It's also got applications to various other areas, robotics, quantum physics, data analysis, medical imaging is a big thing, CAT scans, everything else, and many, many more. And of course, the thing that I'm going to talk about tonight is nanomaterials. So, what I'm going to talk about this evening, I'm going to say a little bit about what nanomaterials are. They're sort of a chemical/physical thing. It's not the definition of them. I mean, they're kind of chemistry, physics. So I'm not going to spend too much time worrying about, kind of the intricate definitions according to physics and biology. But I'm going to talk more about the mathematical sort of implications of what these things actually have to be. I'm going to say what they're used for and why they're useful, and then exactly how we can use this area of algebraic topology to kind of decipher them and understand them a little bit better. Okay, so nanomaterials. Why are they different from normal materials? What makes them nano? It's not that they're very, very small. There's nothing about nanomaterials that necessarily makes them really, really tiny. But what's interesting about them is the structure on a very small scale. Nanomaterials themselves can be rather large. They can be kind of like, for example, your modern bicycles, modern racing bicycles are made out of nanomaterials because they're made out of something called carbon nanotubes. And the point is that on a very, very small scale, on a molecular level, they have been engineered such that the molecular structure is kind of advantageous for whatever purpose it is that they've been designed for. For example, carbon nanotubes are designed to have very strong kind of flexibility and also tensile strength. So not only can they have increased strength, but they can have also increased electrical conductivity and also chemical reactivity. These are kind of very, very clever things which kind of nanomaterials in general can kind of have, and they're sort of engineered by hand to have these structures on a very, very small scale, which, I mean, they're kind of, from a chemical point of view, better than the things that you would find in nature. So, the main things, I mean, the explanation is a little bit vague, it's a little bit hand-waving, but it's better to come up with kind of examples. And the main examples that I'm going to be talking about tonight are carbon nanomaterials, so simply nanomaterials that are carbon molecules only, and these are referred to as fullerenes. So, there's nothing too technical about that word, it simply means that, well, they're nanomaterials that are made out of carbon. It's nothing more sophisticated than that. So these are some of them. If we look at the first one there, that is what's called a carbon nanotube. Now, what we're looking at is actually something that Andy made a brief mention of earlier. He mentioned graphite sheets, which are carbon molecules all attached together in a hexagonal lattice. And in the carbon nanotube, they are all wrapped up into a tube. And it's a graphite sheet that's been wrapped up into a tube. There's nothing more sophisticated than that. And these have got applications to, for example, cancer therapy. And what happens is you insert these into a patient's body, and you can then irradiate the patient's body with a certain frequency, which would not normally do anything, except it causes the nanotubes to heat up. Why should that be useful? The point is that the nanotubes, if you can get them close to the tumours, will heat up and then cause the tumours to deteriorate. Essentially, you can fire radiation at the patient's body, which would not normally do anything, but if you can get nanotubes into the tumours, it will cause the nanotubes to heat up and it will kill the tumours. This is called photothermal therapy, and it's a very, very important and modern kind of cancer therapy. We've also got something called Buckminster fullerenes, also called buckyballs, which are used in the kind of generation of solar panels, and also this kind of very, very, very modern kind of fullerene, which is called a carbon nanobud, which looks, if you look carefully, it looks a little bit like a carbon nanotube, except it's got this little bit sticking out the side. And actually, that is a Buckminster fullerene ball. And it's sticking out the side of the nanotube, so it's kind of a combination of the two. And this has applications across all sorts of different areas. Lots of them have not been kind of really appreciated yet, but the important point about carbon nanobuds is that they have the kind of strength and kind of materialistic mechanistic properties of carbon nanotubes, and that they're kind of they can be stretched, and also kind of they've got very good strength, and then they've also got the electronic properties of Buckminster fullerene. So they have very good conductive properties, and they can also be used in, for example, touchscreens. So this is kind of where I come in. The important thing is, I'm not going to go too much on the kind of chemistry and the physics tonight, but I'm going to try and spend a little bit more time on exactly where the maths helps us understand these things. So this is where we kind of take a big step from chemistry to maths. if we look quite carefully at what I said a nanotube was a moment ago, this is a sort of a close-up model. This is a nanotube which is kind of capped at either end. So this is what we call a closed fullerene. So a fullerene, again, just to remind you, being a sort of nanomaterial that's made out of carbon. It's kind of a roll-up sheet of graphite that's closed at either end. And again, these are the kind of things that can be inserted into a patient's body to, for example, cure cancer. Now, look at the geometric properties of this. Let's not worry too much about the kind of chemical properties, but let's worry about the geometry. We have what is, again, something that Andy mentioned earlier, a hexagonal lattice that's been kind of rolled up. Except we have these caps at either end. So this is a bit of a catch, and it's also closed. So this isn't just a rolled up lattice. This is kind of a closed, almost capsule-like structure. And this has very interesting geometric properties. So now let's imagine that these sort of little circles here are simply vertices or corners of some three-dimensional, what we call polyhedron. So it's simply a three-dimensional shape with flat faces. That's what a polyhedron is. For example, a tetrahedron, a square-based pyramid, a cube, except this is a polyhedron with lots and lots and lots of faces, lots of vertices, and lots of edges. So, as I suggest, that this is essentially a polyhedron with lots and lots of sides. Now that kind of takes us from chemistry to geometry. We're no longer particularly worried about what the chemical properties of these carbon nanotubes actually are. We just know that we have hexagonal faces and also pentagonal faces, vertices and edges. The main thing, and the only chemical fact that we need to know about these carbon nanotubes, and fullerenes in general, is that the faces, which are these kind of, okay, they're not really faces because when it comes to the molecular structure there's nothing there, but we'll imagine them as faces. They can only be hexagons or pentagons. That's it. We can't have square faces, we can't have triangular faces, we can't have anything else. That's what we've got. Okay. Now, to understand kind of why that should be important, we have to go a little bit back, almost kind of 300 years, to a guy called Leonard Euler. Now, he's a guy that lived from 1707 to 1783, and anyone who knows a little bit about history knows that, well, that's a long time. He did pretty well. He got to 76 in the 1700s. He did a lot of stuff. He was a bit of a polymath. He did mathematics, physics, engineering, logician. He was also an astronomer, and he dabbled in some other areas too. His main thing, he did a lot of different stuff. Euler was a big dog. He did all sorts of different things, and he really produced an awful lot of maths. But his main thing was this thing that we refer to as the Euler characteristic. You may also hear it referred to as Euler's formula. And this might not make much sense without me explaining a little bit more. It simply says V minus E plus F equals 2. A more astute observer might say that that could stand for vertices, edges, and faces. Why should that be some kind of relevant formula or anything else? Well, let's look at what a fullerene actually is. The Euler characteristic is actually something which tells us about three-dimensional polyhedra. And a three-dimensional polyhedra is, again, just a three-dimensional shape with flat faces. If you take the number of vertices, you minus the number of edges, and you add the number of faces, it will always equals 2 for any three-dimensional polyhedron. You can play this game yourself. If you pick, for example, a tetrahedron, a square-based pyramid, or a cube, any three-dimensional polyhedron, and you play this game, you will get 2. Vertices minus edges plus faces. Euler discovered this himself. He couldn't prove that that was true, but for any example that he ever picked, he kind of figured out that this must be the case. Now, looking at fullerenes from a geometric standpoint, we get this hexagonal and pentagonal sort of kind of shape. So this is one example of a fullerene. This has only pentagonal faces. This one has a mix of hexagonal and pentagonal faces. And one thing that was actually mentioned just a couple of minutes ago was that, you know, something having too few pentagons. This is either an interesting coincidence or they looked at my slides before before they did their little quiz. Which is there's a fascinating result about any three-dimensional polyhedron. Again, we're forgetting about all the chemical structure of these guys. We don't care. All we care about is that the thing itself is made up of only pentagons and hexagons. If you have a three-dimensional polyhedron where its faces are only pentagons and hexagons, you can say a very, very interesting thing about the number of pentagons that must be the number of faces that must be pentagons. We don't know how many hexagons there are, but we know a little bit more about the number of pentagons. And I don't have to impose any more restrictions. All I have to say is that there are flat faces, it's in 3 dimensions, and that there are pentagons and hexagons only, and nothing else. So, here's the theorem. This is the big kind of, this is a sort of complicated theorem, and in a minute I'll give the kind of the punchline. So, given a three-dimensional polyhedron, there's nothing more complicated to this other than this three-dimensional shape with flat faces, whose faces are all either pentagons or hexagons. This is it. That's all I need to know. I don't need to know anything more. I can say that the polyhedron, via algebraic topology, and in particular the Euler characteristic, has exactly 12 pentagonal faces. It can't have any less, which was their point in the previous quiz, and it cannot have any more. So any polyhedron in 3 dimensions, which has only pentagons and hexagons as its faces, must have 12 pentagons. There's nothing more to it. There's no more kind of complicated, that's it, that's a fact. The punchline here is that any closed fullerene molecule, which as we recall, has only pentagons and hexagons for its faces, has exactly 12 pentagonal faces. Now there's a couple of big things about this. Firstly, that's a result that only came from mathematics. Nobody's used any results from chemistry other than the faces must be pentagons and hexagons. And we have then used maths to kind of, sort of, I don't know, let's say prove the fact that there must be 12 pentagonal faces, regardless of anything else. And here are some examples. I put them on the slide. So these are the two guys that I showed earlier. Here's a few more. This is a guy that looks a little bit like a nanotube. He's got quite a lot of hexagonal faces, this guy in the middle here, and some pentagonal faces, and we know there's going to be exactly 12. And then there's this guy in the middle, and there's a couple more here. Now, what's the big punchline here? I mean, the important point is that I took one fact from chemistry, which is that any fullerene, which is a carbon nanomaterial, or a closed, I should be particular, closed carbon nanomaterial, as in it has caps at either end or has no holes in it. For example, there's no missing faces here. This is not some kind of long, infinitely long tube with no ends. This is a closed thing. For example, if I put something inside it, it wouldn't fall out. It has exactly 12 pentagonal faces. And why is this relevant? Well, it means that when we synthesize nanomaterials, and in particular carbon nanomaterials, so fullerenes, we now know exactly how many pentagons we have to have. There will be no way of synthesizing nanomaterials or fullerenes without having exactly 12 pentagons.
Silly question.
Sure.
Sorry to interrupt. Is it just the angle of view? Or are we talking regular hexagons and regular pentagons?
That's a very good question. So the answer is no. We're not talking only regular pentagons and regular hexagons. We're actually talking any pentagons and hexagons, any six-sided, two-dimensional shape. That's something I'll come more to perhaps in the question period. But yeah, the answer is that yes, of course, I've presented some very nice-looking regular pentagons and hexagons, but no, that's not important. It's the fact that they're irregular. They can be any six-sided, flat, almost two-dimensional shape. And this is kind of the crux of the matter. The fact is that we can prove things about synthesization of chemical materials, so nanomaterials, using only algebraic topology. And whilst this might seem like, if we go back to Mr. Euler and his kind of really abstract looking equation, V minus E plus F equals 2, okay, we're only talking about shapes in 3 dimensions and blah blah blah. Well, we can now realize real information about synthesizing 3-dimensional molecules. And that's important for, I don't know, all the applications that I mentioned earlier, for fullerenes. So nanobuds, Buxminster fullerene, carbon nanotubes, and everything else. And I guess I'll stop there.
Does anyone have any questions? Lots of people have questions. Over there first?
I've not heard of buckyballs being used on solar panels. Can you just quickly say why?
So, expanding on buckyballs being used in solar panels.
Buckyballs have a very interesting property on a physical/chemical level, depending on sort of where you stand, which is that they have an ability when an electric current is induced through a material that has buckyballs as part of its molecular structure, they emit electrons in a way that normal materials don't. This is kind of one of the benefits of having this nanomaterial structure, which is that you can kind of get materials to sort of emit electrons in ways that they normally wouldn't, based on this kind of, if you look at kind of, okay, I'm not going to use the word sort of massive materials, because that'll be confusing, but normal materials, they have a kind of chaotic structure on a molecular level. They haven't been synthesized to have this very regular, for example, hexagonal lattice or anything else. So sort of firing photons at them doesn't do anything. But if you have a material that's kind of laced with these, for example, buckyballs, then they have a higher potential for emitting electrons when photons are sort of incident upon them.
The pentagons and hexagons, when they're joined together, each vertex has 3 edges. And that's down to the valence. How does carbon, the nanopart, fit on? Because then there's going to be these 4 edges.
Okay, so just to be clear about the question, so what you're asking is that, okay, looking at the molecular structure, for example, a nanotube, if you look at one of the molecules in the middle of the nanotube, there are 3 edges that kind of come in, and what was the next part? I'm sorry.
So when you've got the carbon, nanopart,
yes,
stuck on the top,
yes,
at the joining points, there's going to be the edges.
as in at the joining point. Well, when you say at the joining points, exactly what do you mean there? Shall I flick back to the slides? We've got a picture of this thing that we're talking about. So this is sort of okay, here we go, a kind of graphical depiction of a nanobot, yeah? So you say at the joining point, there's going to be more than 3 edges. What do you mean by that?
Are you saying there's an empty gap at the bottom of it?
Yes, exactly. It's almost like the nanobot has kind of been stretched out that way. Yeah? Okay, got it.
So we established from looking at the shape of it, that it must have 12 pentagons. Is there a chemical relevance to the 12 pentagons?
That's an excellent question. So the question was, we've established from sort of looking at the kind of, let's say, algebraic topology or geometry that there must be 12 pentagons. Is there a kind of chemical relevance? As far as I know, and I'm not a chemist, I'm a mathematician, as far as I know the answer is no. That's very, very loose. If you ask a chemist, they might know more. But as far as I know, it is the geometrical properties of these molecules which insist that there must be 12 pentagons. So if you look at this from a purely chemical point of view, you would observe that in these closed fullerenes there must be only 12 pentagons, but without knowing more, you perhaps wouldn't know why.
Does anyone have one last question of Matt? If not, then let's thank all 3 of our speakers again.